Good morning, good evening, or good afternoon, wherever you are. I'm happy to have you back for second lecture on as part of the course called Climate Science, discussion for everyone. This is, let me share my screen here so we can get back to where we were. All right. So we were talking about how the climate works in the last section. You may remember we left off with this drawing of the emission spectrum at the top of the atmosphere, illustrating the greenhouse effect. Our takeaway learnings from that are that the Sun-Earth radiation system reaches equilibrium when the energy falling on the Earth equals the energy that the Earth is radiating away into space. And if it wasn't balanced, the Earth would either heat up or cool down, depending on which way the balance went. So if more energy is falling on the Earth and it's radiating away, it would heat up, and the same is true vice versa. We also said that the greenhouse effect is directly observed in satellite measurements. That was the previous slide I just showed you, and reduces the energy radiated into space at certain wavelengths that are associated with particular molecules, in fact, with the particular vibration pattern of particular molecules, thus causing the surface of the Earth to heat up to compensate for where those molecules remove energy from the spectrum. And that's the greenhouse effect. So now in this section, so that was basically, if we look at the big factors that drive the climate, that was the very first one, and it is the one we spent the most time on. But now we're going to go into some of these other factors. And in fact, we're going to get down pretty much to factor number 6. So we're going to talk about the effects of the Earth as a sphere, the spinning of the Earth, the land and the oceans, the effect they have. Because this is all going to lead to how energy is circulated around the Earth's surface, right? So we're going to spend some time on that. And basically, this is the large scale. We're going to worry about the large scale structure of the climate and its circulation on the Earth. So the first thing we notice here is that this graph shows the energy distribution by latitude. So you would expect that because the Earth spins, if it weren't tilted, basically in longitude, we'd have pretty much the same distribution of energy. The fact that it's tilted makes a slight difference. However, the big effect is going to be in latitude just because the Earth is a sphere. You can prove this to yourself just by saying, if you take a flashlight and point it directly down, you'll see a spot of light. If you tilt it at an angle, you'll see that that spot of light spreads out. In other words, the energy intensity per unit area is less, all right? And that happens in the Earth. Basically, the flashlight is the sunlight coming to the Earth. However, the Earth's surface is curved, and this curve basically corresponds to you tilting the flashlight. So if you look at this drawing, again, the left-hand side has a fancy name, radiation flux density, but what you should really read it as intensity, right, in watts per square meter. And the bottom axis is in latitude. So at 0 is the equator. If you go to 0 and then go straight up, you'll see that the darkest black curve, it's a little hard to see on this drawing, but the curve that's on top at 0 is basically the energy incident on the Earth's surface, right? And so the incoming, that is the incoming solar energy. And if you trace that curve down at 45 degrees, it goes below the flatter curve. The flatter curve is the emissions energy by latitude, right? And you notice an interesting thing. The emissions curve is low in the center, then goes up to about 30 degrees north and south, actually more like 20, and then goes down as you approach the poles, right? But when you get the poles being at plus and minus 90, But basically, what it says is that there's an energy surplus between 30 degrees positive and 30 degrees negative. To give you a feeling, here in Tallahassee, we're at 30 degrees positive, right? 60 degrees positive would be a place like Oslo, Norway. In Oslo, Norway, if you look at 60 degrees positive, there is less energy coming in than there is going out. And the reason that happens is because energy gets moved to Oslo by circulation in the atmosphere and the oceans, right? So from about 45 degrees out, there is an energy deficit. In other words, more energy is radiated than is away from the Earth than is received. And between 45 and minus 45, more energy is received than is radiated. All that to say that the energy is moved from the equator to the poles, and the poles act as radiators to cool the planet, all right? The next slide just has a little more information about the structure of the atmosphere, because we're going to need to talk about this in language. The atmosphere has named layers. So the troposphere is the lowest layer. This is where all the weather exists. And when we say the surface of the Earth is warmer, we mean the immediate surface, measured, let's say, at 10 feet above the ground level. We mean the top, maybe 1,000 meters of the ocean. Basically, this graph on the left shows the structure of the atmosphere. So if you look, the scale on the bottom is the temperature, and it goes negative. In other words, it goes up. It goes down in temperature as you go up. Something about 6 degrees per kilometer, 6 degrees centigrade per kilometer. But basically, you can see that it goes from 20, maybe 60 degrees Fahrenheit or 20 degrees centigrade. And as you go up the troposphere, it drops pretty dramatically to something like minus 60 degrees centigrade or minus 80 degrees Fahrenheit, right? Then there is a section called the tropopause, which basically is pretty much constant temperature. And then in the stratosphere, the atmosphere actually warms up and gets back to about 0 degrees centigrade. And the reason it warms up is that the ozone has a maximum density in the lower stratosphere, and it absorbs a lot of ultraviolet energy coming in from the sun, and then heats the stratosphere. And so it goes back up. And then the layers above that we don't really need to worry about. They're not going to be relevant for this course. They are called the mesosphere and the thermosphere, but we don't need to worry about them. What we need to say is that the troposphere is kind of up to 10 kilometers, which is like 6 miles, a little over 6 miles. Then the stratosphere takes over and goes up to maybe 50 kilometers, maybe something like 30 miles. The graph to the right shows that the air pressure and density are going down exponentially, right? This is a logarithmic scale along the bottom axis. So it drops, the air density drops off, the air pressure drops off very quickly as you go up. Now, the height of the troposphere varies from the equator to the poles due to thermal expansion. So basically, at the equator, the troposphere is larger than it is at the poles. Now, the next thing we said, the next big factor in the Earth's, driving the Earth's climate is the spin. And to understand what effects the spin has, we have to first understand what's called the sea breeze. So if this is not a spin effect, this is actually an effect due to land and water, but it's going to be a very simple model for what we're going to use for atmospheric circulation. So we need to understand this. If you look at this drawing, the sea breeze if you stand on land during the day, let's say early afternoon, you are likely to feel a sea breeze of cool air coming off the water into your face as you look out to sea, right? And the reason this is the case is because the land, as we've said before, heats up faster. And when it heats up, it shares that heat with the overlying atmosphere that it's in contact with. So basically, the air over the land that you're standing on starts to expand, and you get a lower pressure. When I mean expand, it basically air starts rising, and so the pressure goes down on that spot. That air going up then ends up raising the pressure at a altitude above your head, quite a ways above your head. But because it's low pressure, over the cold water, over the water, which is cooler because it does not heat up as fast, the pressure's higher. So that basically the breeze, the wind, always blows from high pressure to low pressure. So there's higher pressure over the cold water out to sea, the direction you're looking. It blows air towards the low pressure on the land where you're standing. And that, when the wind blows air towards the shore, air comes down from above to fill up the spot, basically to replace that air. So you end up with this circulation. It's named after a person, Hadley, the Hadley circulation, and it explains the sea breeze. You can get a land breeze where land air is coming off the land and heading out to sea. Now, this little circulation is going to become important. What we need to take away from this curve is that wind blows from high pressure to low pressure, and that you can get high and low pressures depending on differences in temperature of the surface near those, okay? Now, back to the Earth spins. The Earth spins, and what you might know is that because we stand on a solid object, you see these different folks here. There's one guy here, he's standing at various latitudes on a solid object, right? The diameter of the Earth is 8,000 miles. In 24 hours, you're going to traverse a circumference of 8,000 times 3.14, which is pi. You're going to basically go around essentially 24,000 miles in 24 hours, right? So you're going to go 1,000 miles an hour, right? This units here are in kilometers, so 1,650 kilometers an hour corresponds to 1,000 miles an hour. However, if you're standing somewhere else, as you get closer and closer to the poles, you're going around slower. So you're going around the surface of the Earth slower because the radius of your circle is smaller, right? And so basically the atmosphere is circulating with you. The atmosphere is a very thin layer. And you might wonder, does the atmosphere turn at the same rate as the Earth does? And the answer is yes, near the surface. As you go up, you can get some vertical shear, but typically most of the atmosphere, which is very thin compared to the radius of the Earth, goes around at the same velocity. If it didn't, for example, if the atmosphere was still and the Earth spun in it, you would be at the equator experiencing 1,000-mile-an-hour winds, right? And hurricanes are 100, 150 is a big hurricane. We don't have 1,000-mile-an-hour winds, so the atmosphere is turning with us. What that means is the atmosphere is turning slower as you go to higher latitudes, right? Now, this leads to a complication in moving energy from the equator to the poles. So what you might expect is, if you think, I'm going to go back a slide, if you think about the Hadley circulation, let's put the equator at the low pressure end of the Hadley circulation, basically over a hot part, whether it's water or land, we won't worry about too much. And let's put the North Pole at the high pressure end of this curve, where it says cold water today, but we're just going to say North Pole, right? Well, basically what should happen, we should get a pole breeze, a polar breeze, going from the high pressure North Pole to the equator. And then we should get this full scale circulation. We should basically have one big Hadley circulation from the pole to the equator. The warm air would be carried back to the pole by the high pressure. In other words, the warm air would go up at the equator, ascend, and be carried back to the pole at the top part of the Hadley circulation. And that's how the pole and the equator would presumably try and equilibrate their temperature, right? That's what's really going on here. The circulation on the Earth is trying to basically make things the same, even though they're different because of the spherical shape of the Earth. However, the spinning that I just talked about on this slide makes that more complicated. It doesn't allow us to have one simple circulation like the sea breeze. So what do we get? We get this thing. So this thing, by the way, is a model of the circulation from the equator to the pole. Now, this model is not perfect. We're going to explain in a minute that it has some issues having to do with land and ocean heating up at different speeds. However, this is a pretty good approximation and explains a lot of structure in the atmospheric circulation. And what you notice is there is Hadley circulation. There is a Hadley cell. So at the equator, we show air ascending, right? And basically, we show circulation that tries to move air from 30 degrees north. In other words, if you think about this, because the air is ascending at the equator, we have low pressure. At 30 degrees north, and take Tallahassee, Florida as an example, we're at approximately 30 degrees north. Air, it's cooler here than it is at the equator. So air tries to move from the high pressure that's here to the low pressure at the equator. So the surface current goes from north to south. Then the air ascends, and basically fed back at the top is warm air coming back at higher altitudes in this Hadley cell. Now, it turns out if you go up to the North Pole, you have a very similar situation. The pole is cold and high pressure at the surface relative to 60 degrees north, let's say Oslo, Norway, right? So basically, air tries to move from the North Pole to Oslo, Norway. It ascends there in Oslo and circulates the way I've drawn it, right? By the way, the arrows coming down are rain. So because the air is ascending, it precipitates and rain falls out, right? So that's not wind coming down. That the circulation is counterclockwise if you look at your screen, as is the Hadley cell. So both the polar cell and Hadley cells are counterclockwise with the surface wind blowing to the south, right? In between these two cells is a third cell called the Ferrel cell. It's weaker, but it's basically a cell that goes from 30 degrees north to 60 degrees north, and it's driven by the other two cells where the temperature contrasts are stronger. The Ferrel cell is, for example, where most of North America lives. I told you my house in New York is at 43 degrees north. You have to get into Canada to get to 60 degrees north. And so basically the Ferrel cell lives between these two strong cells. The reason that these cells get broken up into these pieces, if you think of these as convection cells, which is what they are, they're broken up because of the spin. The spin doesn't allow us to have one Hadley cell all the way to the pole. You'll notice that there is the famous polar jet, or the jet stream as sometimes call it. Some people, the cold air above the jet stream, the cold air from the jet stream north to the North Pole is sometimes called the polar vortex. You may have been reading about that lately. There is also a subtropical jet that's not as strong as the polar jet. Notice that the direction of the polar and subtropical jets are into the page. In other words, going east as we look at the equator to our right. These directions are related to conservation of angular momentum in perhaps a slightly complicated way if you tried to work through all the math involved in showing that. But what we can say for our purposes is that the cells, the circulation patterns in these three cells drive the jet stream in combination with the Earth's rotation. That complex set of forces, including the Coriolis force and the pressure gradient force that's trying to drive energy from the equator to the poles, generates this complex situation. We should also say that the strength of the jets depends a lot on the contrast of the temperature across the cell boundaries. So one of the reasons the polar jet is so strong is that the polar temperature is a large gradient, large change in temperature between it and the ferrule cell. And so that's partly why it's strong. We'll talk later in the course a little bit about some evidence that it might be slowing down because, as we know, the polar region is actually warming up faster than the rest of the Earth. But we'll get to that, patience. We should also note the angle on the top of the drawing. That is the height of the tropopause. I think I might have mentioned earlier, the equator, since it's warm, the air is, in a sense, expanded. It is expanded. So the height of the tropopause is higher. And as you move towards the pole, it's colder air. And so the height of the tropopause is actually lower at the pole. And that's expected from where we are. One of the things this leads to is a very interesting, this rather complicated drawing. Sorry about how complicated this looks. It's really not that complicated. But basically, think about the fact that earlier we talked about the trade winds and the westerlies. What happens in this circulation is that if you're at 30 degrees north and you are a parcel of air moving towards the equator, you start out at a velocity, let's say around 1550 kilometers per hour, right? Which is actually something like, I have it on one of these drawings, I have the number. It's actually around 960 miles an hour instead of 1023 at the equator. So as that air moves south towards the equator, to an observer at the equator, that air is moving at 962 while he's moving at 1023. As a consequence, it looks like that air that is coming towards you is moving to the west. That is how the easterlies arise, right? So think about that this way. If you're in a room and you picture a chair or something across the room for you, pretend that chair is at Tallahassee and you're at the equator. As that chair gets pushed towards you because it's at higher pressure, so the pressure gradient force, the force that comes from the fact that at Tallahassee the surface pressure is higher than at the equator, that air comes towards you. It's also moving to the east slower than you are. You're moving to the east at 1,000 miles an hour. It's moving to the east at 960 miles an hour. It looks to you like it's going towards the west. In other words, it looks like an easterly wind, right? Easterly wind comes from the east, heads to the west, right? Now, if you think of the ferrule cell has surface, the pressure gradient force wants to push air from 30 to 60, right? So in so doing, it's pushing it from a higher velocity going east to a lower velocity going east. So it looks like it came from the west and is heading east, right? Faster than a person standing at 60 degrees north. That's why you get a westerly in the Ferrel cell. So what you get at the equator is, just look at this sphere for a moment. Off to the left are some drawings that show the pressure gradient forces and the wind velocity change as this spinning Coriolis force takes over. But it's simpler probably just to think about the analogy I just said. If you look at the sphere, the rough sphere, it's pretty roughly drawn, isn't it? It shows at the equator northeast trade winds, right? And the reason they go northeast, remember the wind is named from where it's coming from. The reason it's called northeast is because at the equator, there's enough friction because the Coriolis force isn't as strong. They tend to converge on the equator. But they're trade winds, right? They blow from the east to the west. The westerlies are in the Ferrel cell. And then when you get to the polar cell, it goes back to being easterlies again because the air is moving from the pole, which is hardly spinning at all, to 60 degrees north, which is spinning a lot faster than the wind coming from the pole, right? So that's how you get these. Now, these winds are called geostrophic, if you want to write down a fancy word, or they're also called zonal, Z-O-N-A-L, like in a zone. Here's a picture of Columbus's trips to America, all of them. You notice on the first voyage, what Columbus did was what people did in his day. You basically went south. When you left Spain, you went south till you picked up the easterlies, and then you got your path over to India, right? Which turned out not to be India. You got your path over there on the easterlies, and then when you went back, you tried to get far enough north that you picked up the westerlies in the Ferrel cell. That's something we said earlier as a climate question we would try and explain. Now you notice once or twice he went back without going very far north, and that took a lot of tacking, and those trips took longer to take. If you look at hurricanes, hurricanes form in the Atlantic. These are hurricanes, not typhoons. Basically, both hurricanes and typhoons are tropical cyclones. The ones in the Pacific are called typhoons. The ones in the Atlantic are called hurricanes. These are hurricanes, and they form, these are the paths of hurricanes. They form in the on the equator in the Atlantic Ocean. They head east on the, they head west on the easterlies. It's hard to say that. And as they start heading up, they end up running into the Ferrel cell and turn back towards the east, being driven by the westerlies. Now, hurricane tracks are complicated by high pressure ridges and things like that are also part of the circulation, more complicated circulation system. So what I just told you is only generally true. But you can see in general, it pretty much corresponds to almost all hurricanes eventually run into the westerlies of the Ferrel cell. Okay, well, one of the things you would say, given this drawing of the circulation, you would say, well, we have ascending air at the equator, which means that moisture in the air will go up because it cools as it goes up. It precipitates out as water, and it falls as rain. So we should expect clouds at the equator and a lot of rain. That's what we get. When you come to 30 degrees, we have descending air. This air has already had the precipitation scrubbed out of it. So we would expect dry air to be coming down at 30 degrees north, right? So if we look for here is a satellite picture of the Earth from the European Space Agency on a particularly clear and beautiful picture. You'll notice that at 30 degrees north, we have a band of deserts going across the picture. And at 30 degrees south, Australia is basically at 30 degrees south, The Sahara is 30 degrees north. Some of it's the equator. You can see the equator is kind of the green space in Brazil and at the bottom edge of the desert in Africa, right? And so you see deserts at 30 degrees north. Now you see other things at 30 degrees north that aren't deserts because they're affected by the way the circulation works with local water sources. Like the Gulf of Mexico keeps the southeast United States fairly green because of storms coming off the Gulf. The other thing you expect is, or see, is this band of clouds across the equator. This is the effect of the ascent at the equator. It's also called the Intertropical Convergence Zone, if you want a fancy name, the ITCZ. And basically, it does move with the seasons. So it goes north in northern hemisphere summer, and it moves south in southern hemisphere summer. But you will see this band of clouds around the equator where we get the circulation moving from the warm surface and land up to the surface waters and land into the atmosphere. Okay, now we also get energy distribution from the oceans. And I'm not going to go into the full physics of this. It's not that much more complicated than the atmosphere, but basically it takes a little time to explain. But basically the oceans have what are called, these are the surface currents. What you're looking at here is the surface currents. And these have what are called gyres, G-Y-R-E-S. They're basically like cyclonic whirlpools, right? Like you see whirlpools. Take a look at the Atlantic. If you look at the Atlantic over here, you'll see that the circulation in the Atlantic Ocean is clockwise. And now if you go over and look at the Pacific, you'll see in the northern hemisphere, you'll see the circulation in the Pacific is clockwise. If you go into the southern hemisphere, you'll see that the circulation in the Atlantic off of Brazil is counterclockwise, and the same is true off of Australia. These circulations have to do with the spin of the Earth, the Coriolis effect. We won't go into the details of that, but basically they create energy movement in the water, which circulates energy. If you look, you can see the Gulf Stream forming off the southeast United States coast and heading across. You can also see the California current on the west coast coming down along the current, bringing cold water down from the north, right? Our question about California and Dallas, why are the climates different? The California current keeps Los Angeles cool. It brings cool water down along the coast, cooler than might be expected from that latitude. And it also, because it is west of the city of Los Angeles, and Los Angeles is high enough up in latitude that it gets a westerly current, westerly airflow off the ocean, and the ocean doesn't heat up that fast or cool down that fast. You get a moderated temperature. Dallas is a continental city, so it is essentially in the continent. It's not that far from the Gulf of Mexico, but it's far enough. And the wind doesn't the wind brings currents from the land. So in Dallas, you'll get in the winter cold air masses moving down from Canada, and so it gets cold, actually snow in Dallas. But in the summer, you can get very hot tropical air moving from the Gulf of Mexico. And so its climate is not moderated like Los Angeles is. Okay, so that is one kind of ocean circulation. But you also have another very important ocean circulation, and this is called, the simple name is the deep ocean circulation. It's also called the thermohaline circulation. By haline, you should think of salt. And basically what happens is if you come up here by Greenland, there's cold water there, which means it's denser. and salty water. So basically the water here tends to sink to lower depths in the ocean because it's denser than the water that is around it. It sinks and then proceeds down in this big loopy pattern in a deep cold current and resurfaces again over as part sort of underneath the California current and comes slowly to the surface and warms up as it passes through the equator on both sides of Africa, comes back north as the undercurrent on the Gulf Stream, bringing warm water and climate to places like England, and then completes the circuit, right? This is another very important ocean circulation that carries energy, helps carry energy from the equator to the poles. And one of the questions, of course, is this depends critically on the density of the water. That's how you get the sinking. The rotation of the Earth causes the currents in the ocean because of the rotation causes the Coriolis effect force to act. But basically, it depends on those two things. That's why it's called thermal haline. So basically, what we have covered in this section is the circulation of the energy from the equator to the poles. And so what you get is you get an atmospheric contribution to that. Energy is conveyed around the Earth through these systems that arise in both the atmosphere and the oceans. And these systems create big effects on not just the overall climate in terms of the three-cell model and the position of deserts on the Earth and the position of rain bands and precipitation, but they also affect local weather because of the way in which the atmospheric circulation brings warm or cold air and the way in which the ocean circulation moderates the temperature of coastal cities or internal continental cities. So that is that section of the course. That's part 2. We have one more section of the course that has to do with basic climate before we get into some of the other climate questions we're going to get to. Thank you for spending time with me here, and we will move on to the third section as soon as you get a chance to see it. Thank you.